Okay, so today we will discuss some of the nonlinear application of the operational amplifier. Nonlinear application means the output voltage and the input voltage relationship is not linear. Not linear means linear relationship is suppose output voltage is V0, input voltage is V1. So V0 must be proportional to V1. That means V0 must be some constant into V1. So that is the linear relationship between the output voltage and the input voltages. Now whenever we discuss the nonlinear applications, so nonlinear applications means the output voltage is not proportional to the input voltage. Okay, so there is a nonlinear relationship exists between the output voltage and the input voltage that we will discuss today. So the circuit we will discuss, that is the integrator circuit. Now I am just drawing the integrator circuit. So in the case of the integrator circuit is nothing but your inverting amplifier, and in the case of the inverting amplifier, the feedback resistance RF is replaced by a capacitor. That's it. If you replace the feedback resistance RF in an inverting amplifier with a capacitor, then integrator circuit actually generates. So I am just drawing the circuit. So this is your negative, positive, and this is the input voltage with a resistance. So this is the input voltage and this is the resistance R1, and in the case of the inverting amplifier there is a feedback resistance. Here happens to be a feedback resistance, and this is the output voltages, and this is here obviously grounded. So here in place of the feedback resistance, here we connect a capacitor. So that's your circuit. Okay, and the current flowing through this R1 path is obviously I1 in the analysis path, and the current flowing through this capacitor we will discuss as IF. Okay, so you can see from the circuit diagram that this circuit is exactly equal to the inverting amplifier with a small difference with the capacitor with the feedback resistance. Now the current flow through the R1 in the analysis part is the same. Analysis path we will follow the same procedure. That means I1 is equal to IF. Okay, so that is the procedure for every analysis of your linear. Whenever we discuss the linear application of the operational amplifier, then we discuss this procedure as same. Okay, so I1 here, in the case of the I1 is nothing but this voltage is and obviously this operational amplifier is ideal one, and this is the operational amplifier, this is the ideal operational amplifier, and gain of the operational amplifier is obviously open loop gain is infinite, so that we can apply the virtual ground concept. So the virtual ground concept means this potential is 0 volt, so just this potential is also 0 volt. So the current flowing through the resistance R1 is I1, so I1 is equal to nothing but V in input voltage. This voltage is nothing but the input voltage minus 0 divided by R1. So non-inverting terminal is at a ground potential, that means node A will also be at the ground potential or the virtual ground, so that this potential is 0 volt, so this V in minus 0 divided by R1. Okay, so now we will write the equation for the IF. So the equation for the IF will be equal to, IF is nothing but current through the capacitor is C dV dt. Okay, so current through the capacitor, so this is a capacitor. Okay, so this is okay, so the current through the capacitor is actually, whenever we discuss the current through the capacitor equation, I equal to C dV dt. Okay, so this is the current through the capacitor equation. Now just analogy with this equation, we will write this equation, that means IF equal to C, value of the capacitor is C, and dV is the difference between the voltage that is two terminal. So two terminal is capacitor, two terminal, this terminal is 0 volt, this terminal is V0. So d VA minus V0 divided by dt. So VA it as 0, so C minus C dV0 divided by dt. Okay, so this is the equation for the current flowing through the capacitor. Now just I am equating both this, I1 equal to IF. Okay, I1 equal to IF. So if you just equate I1 equal to IF, so this is V in divided by R1 equal to minus C dV0 divided by dt. So dV0 divided by dt is equal to minus 1 divided by R1 into C into V in. Okay, so integrating at the both side, if we just integrate at the both side, then this dV0 by dt with respect to 2 differentiating both side, then this will become your V0t. This will become V0t. Okay, because suppose there is a term x, and if we just differentiate this dx dt, and if we just integrate this, we will again get back this. Okay, so this is the procedure followed here. So dv0 dt, just like a sine, there is a sin x, so differentiation of sin x is cos x, and the integration of cos x is here also sin x. So the v0t is equal to minus 1 divided by r1 into c into integration into v in into dt. Okay, so this is the procedure, and negative sign is there. Negative sign is for the inverting amplifier case. Now in this case we have assumed that the capacitor is initially discharged, that the voltage initially stored in the capacitor is 0. Now if the initially stored voltage in the capacitor is there is some amount of voltage, then the final expression for the v0t is 1 by r1c into integration v in dt plus v0 at 0 time. Okay, so this is the final expression for the v0 to v0 0, that means at time 0 there is the initial voltage v0. This is the initial output voltage or the stored charge inside the capacitor. Therefore this circuit provides the output signal which is the integral of the input voltage. Okay, so this is the perfect example of an integrated circuit, and you can study few of the example or the numerical example based on that how the output voltage will look like, apply a sinusoidal input voltage or something like that. Okay, so next circuit we will discuss is the differentiator. So next we will discuss the differentiator circuit. Okay, so differentiator circuit. Okay, so circuit of the differentiator circuit, if we just in the case of the integrator circuit, if we just interchange, suppose this is your integrator circuit, so if we just interchange the position of this resistor and the capacitor, then it becomes an differentiator circuit. So the differentiator circuit is look like this. So this is your negative, this is your positive, this is your output voltage. So capacitor, this is your input voltage, so capacitor will come here. Okay, this is your input voltage and the resistance will come here. Okay, the resistance will come here. So this is your resistance, this is your capacitance. So we just interchange the resistance and the capacitor in the case of the integrated circuit. So it becomes the differentiator circuit. So you can see that this is the input voltage and this is the capacitor, and current flowing through this capacitor circuit is I1, and current flowing through the resistance is IF. Okay, so the same concept, the op-amp is ideal, and the open loop gain of the operational amplifier is infinite, so that we can use the virtual ground concept. So due to the virtual ground concept, this potential is also 0 volt. So applying KCL at this node, this is the node, so applying KCL at this node, we can found that I1 is equal to IF So your I1 is nothing but again C dV dt. So C, this I1 is nothing but C d V in minus 0 divided by dt, so dt V in dt, and your IF equal to 0 minus V0, that means minus V0 divided by R, 0 minus V0 divided by R. So if you just equate these two, then C dV in dt equal to minus V0 divided by R. So your V0 will become minus CR dV in by dt. So in the both the application you can see that the input voltage and the output voltage is related by the differentiator. So this is the relation. Okay, you can see the input voltage and the output voltage, the relationship between is that the differentiation. So that is the application we are looking for. We want that from this circuit. Okay, and in both this application the output voltage and the input voltage are not in a linear relationships. So the output voltage is proportional to the derivative of the input voltage, and so if V in equal to sin omega t applied at the input terminal, then the output voltage will be cos omega t minus CR omega cos omega t. This means the output voltage is proportionally increased linearly with the signal frequency. So that is the application of the operational amplifier in the case of the differentiator circuit. Okay, so both these two applications are the nonlinear application. So the next nonlinear application that we will discuss is the log amplifier. Okay, so this is the log amplifier. Okay, where the relationship between the output voltage and the input voltage is logarithm. Okay, in the previous two cases the relationship between the output and the input voltage of the differentiator and the integrator, just like here the relationship between the output and the input voltages are log. Okay, log relationship, log dependent relationship. Okay, so these log amplifier also a nonlinear application of the operational amplifier, and in the case of the logarithm amplifier, the output voltage is directly proportional to the logarithm and the input voltage. That means the output voltage proportional to the log of the input voltage. That's the relationship we want to establish through the circuit, where Vi in the input voltages and your V0 is the output voltages. Now when the linear operational amplifier is combined with the nonlinear device such as an diode, transistor, log amplifier can be achieved. That means with the operational amplifier, till now we have discussed the application where with the operational amplifier we have connected only the linear device, that's the resistance, capacitance, like that. Now here in the case of the log amplifier, we will connect a nonlinear device. That means that nonlinear device may be used here. We will use a transistor with the operational amplifier. Then we can establish a log amplifier out of this circuit. Okay, so the circuit, I am just drawing the circuit. The circuit will look like this. Circuit will be the same, just like the inverting amplifier. This is your negative, this is your positive, this will be your ground terminal, and the feedback path. Okay, this feedback path is important. Here the feedback path, there is a transistor connected like this. 1 minute. So this is your emitter terminal. Okay, and this is your output voltages. So your transistor will be connected and your base will be grounded like this. So this is your collector. You can see this terminal is your emitter terminal, this terminal is your emitter terminal, this is your collector terminal, and this is your base terminal. Okay, so this is your base terminal. So this is your emitter, this is your base. So there is a voltage relationship between these two. So this is positive, this is negative, so the voltage exists here is VB. Okay, So base to emitter voltage, and this is obviously your collector terminal. And in the case of the inverting amplifier, suppose there is an input voltage and there is also a resistance there. So there is an input voltage and there is a resistance. Okay, so the circuit will look like this. There is a transistor and the base of the transistor is so this will be your grounded base, and this will be your collector terminal, this will be your emitter terminal, this will be base terminal. So in the feedback path there is a transistor is connected, and the base to emitter voltage, this is the base to emitter voltage of the transistor, this is the output voltage. So this is all about the circuit diagram of this operational amplifier. So as the virtual ground concept is also applied here, so this terminal is grounded, this terminal is grounded, so that this potential is also at 0 volt, potential at this point is also 0 volt. Okay, now the emitter transistor emitter current, what is the emitter current? We have studied in the case of the transistor. In the case of the transistor, so this is all about the transistor. Now we will discuss the transistor. So the current through the emitter is the, this is your BJT, this is your emitter base collector. So this emitter and the base terminal is forward bias as always. So as this is forward bias, current is just obeying the diode relationship. So in the case of the diode, current is, this is the reverse saturation current into e to the power, you just cross check this equation. Okay, e to the power q into VB, this is the forward bias voltage, okay, divided by kT minus 1. So this is the equation for the diode equation, diode current equation, and that also applied in the case of the emitter current, because diode emitter to base terminal is the forward bias current. So I is the emitter current, and the IS is the emitter saturation current or the reverse saturation current you can call, and K is the Boltzmann constant, T is the absolute temperature. Okay, IS is the reverse saturation current, Q is the charge of an electron. So these are the all parameters associated with this, and VV is the forward bias voltage. Now as base of the transistor is grounded, we can assume that, or we can assume that the base current is very much minimal amount of current. Okay, so that I is nearly equal to IC. Okay, so I is nearly equal to IC. So you can just, base of the transistor is the grounded, or we can see that the current flowing through the base terminal is very much small, so that we can assume that I is nearly equal to IC. So as I is nearly equal to IC, so this IC will be also this same IS e to the power Q into VB divided by KT minus 1. Okay, so this is your equation for the IC. Now we are just going to simplify this equation, dividing both sides by IS. This equation, okay, dividing both sides by IS, so this become IC divided by IS, and this side become just this IS will vanish, so e to the power Q into VB divided by KT minus 1. Okay, so IC divided by IS plus 1 into e to the power Q into VB divided by KT minus 1. Okay, so this is the equation. Now in the case of this IC, this is the reverse saturation current, and this is the forward bias current of the diode. Okay, you can see from here, this is the forward bias current, this is almost equal to EC, and the reverse saturation current. Now the reverse saturation current, all of you know that the reverse saturation current magnitude is very much small, so we can assume that the IC is very greater than IS. Okay, so as IC is very greater than IS, so what happens, we can just ignore this one. So IC by IS equal to IC by IS is just okay. So here I am just this one will not here because this one will come here. Okay, so in this side this one has come in this side. So IC by IS equal to e to the power Q into VB divided by KT. Okay, so this is the approximation. Next, and now taking log on the both side, I am just taking log on the both side. So with base E, so log IC divided by IS equal to E will vanish QVB divided by KT, because log e to the power A equal to B, so e to the power B equal to A. Okay, so this is the procedure. We are just following down in this equation. We just take log on the both side, then this will become, if we just take log on the both side again in this equation, then this will become B equal to this. Okay, B equal to this. This is the procedure we have followed here. So VB, just calculating VB from that equation. So VB is nothing but KT by Q log IC divided by IS. Okay, so this is the expression for the VB. Now the current flowing through the R1. Now the current flowing through this R1 terminal. Okay, this is your R1. So current flowing through this R1 is nothing but I1 is equal to your IC. IC is nothing but this. So this is your IC. Okay, this is your I1. These two are equal. So I1 equal to IC equal to V1 divided by R1. So VB we are just replacing this IC with this V1 divided by R1. So KT divided by Q log V1 divided by IS into R1. Okay, since the BJT is connected to the output of the operational amplifier, the output voltage is equal to V0 equal to minus VB, because the output voltage relationship between the input voltage in the inverting amplifier is the negative relationship. So the output voltage is nothing but KT by Q log V1 divided by IS by R1. So IS by R1 we can consider as V reference. This voltage, this IS into R1 we can consider as V reference. So V0 relationship between the, this is the input voltage, V1 is nothing but the input voltage. Okay, so relationship between the output voltage and the input voltage is proportional to the logarithm of the input voltage. Okay, obviously proportional. There are some of the disadvantages of this circuit. First disadvantage, in the output voltage depends on the temperature. You can see here is the temperature. So the reverse saturation current and the reverse saturation current, so that is the problem. The emitter saturation current varied from one transistor to another transistor in its magnitude, so it depends on the temperature. Therefore the temperature effects on the amplifier performance and the accuracy of this effect can be reduced by temperature compensation. So you have to employ the compensating circuit to minimize the effect of this temperature, because there is a temperature term associated here. So this temperature term creates a problem because this is not the temperature independent circuit. So if we just increase the temperature, some of the performance of the circuit can be changed. So then you can employ the some of the compensating circuit to compensate this kind of effect due to the temperature. Thank you.